A mathematics teacher, Mr. Ulam, devises a new game that uses 4 standard dice. A player rolls all of the dice. Any dice with a 1 facing up are winning dice and are removed. That's an important point. We're going to come back to that. The remaining dice are rolled again. The game is finished when a player has 2 or more winning dice. So they've seen 2 or more 1s. Using the experimental data above, estimate the probability of winning in exactly 2 rolls. So, probability of x being 2, we can see 2 rolls is just there, 113. So that's going to be 113 over 500, giving us 0.226. Not winning in 2 or less rolls. So, the probability of winning in 2 or less rolls is going to be 1 roll, add 2 rolls, divided by 500, and that gives us 0.358. Therefore, not winning in those 2, or winning in 2 or more, is just going to be 1 take away 0.358, which is 0.642. State 2 reasons why the game cannot be modelled using a binomial distribution. Think about the binomial. The binomial always has a fixed number of trials. Our situation doesn't. The player just keeps going until they win. So that's one of the things to write down. It has a constant probability of success, which this one doesn't because we removed the die. I said I'd come back to that. So there's 2 reasons. You could also make an argument that the trials are not independent. Again, the removal of the dice is going to change things and so on. So, Mr. Ulam uses a computer to simulate 10,000 games to better estimate the probability of each outcome. The results of the simulations are summarized in the table below. I'm not going to go right through that. We'll pick out what we need. To fundraise for a local charity, Mr. Ulam charges $1 for each game and pays out winnings as follows. If the game is won in 1 or 2 rolls, the player wins $2. So that would be a gain of 1. If the game is won in 3 rolls, the player wins $1, i.e. they get their money back. That would be a gain of 0. If the game is won in 4 or more rolls, the player wins nothing. So in other words, they lose 1. Let y be a random variable denoting the profit for a player who plays a $1 game. Using the data above, complete the probability distribution for y. So y can take the values -1, 0, or 1. So how do we get the 0? If the game is won in 3 rolls, so that is 0.208. So 0.208 for that one. If they win in 1 or 2 rolls, then they get $2. So 1 or 2 rolls is the 0.134, the 0.215. Add those together and we get 0.349. And then to get this one, we can just do 1 take away the other 2, which is 0.443, because these things need to add up to 1. Okay. Calculate the expected value of y. So the expectation of y is going to be 1 times 0.349 plus 0 times 0.208, take away 1 times 0.443, which is equal to negative $0.094. We want the variance of y, and I always like to use, I don't like what they've done in the mark scheme, I always do variance of y is the expectation of y squared, take away the expectation of y squared. So that is going to give me 1 times 0.349 plus 1 times 0.349, that one there being negative 1 squared. Oh no, sorry, this one is 0.443, and that one there is the negative 1 squared, and then take away 0.094 squared, and if we do that, then it is 0.783. In the long run, do we expect the game will be profitable for the charity? Justify your answer. Well, the answer is yes, and we need to justify. Well, if we look at the expectation for the player, it is negative, and therefore the player is losing, which means the charity is winning.